Hello everyone, this is Sarmad and in this video I am going to do a problem solving session on some of the end of chapter problems of chapter number 6, which is on the physics of MOS transistor. So let's just move on. So the first question that I have is question number 19, which is this. So in this question I've got 4 parts and I have to determine the mode of operation of all these 4 transistors. Just to give you a value of VTH for all these transistors is 0.4 volts. Now let's just take the first one. Here we can observe that this is an NMOS device whose gate is connected to the ground. So we have VG equal to 0 volts. Now out of these two terminals we have to decide which of these two terminals is drain or source. So we can see that as the arrow is heading outwards, so this is an NMOS device, and we know that for the case of NMOS, the source is at lower potential than drain. However, in the case of PMOS, the source has to be at the higher potential than the drain. So now, looking at this figure, you can see that this terminal is at lower potential. So we can call this thing as source, and you can call this terminal a drain. So now we can find the VGS, which we can see it turns out to be 0 volt. Now as VGS is less than VTH, as VTH is 0.4 volt, therefore the device is off. Now moving to the part B, here we can see that the gate terminal is again at 0 volts, and we need to decide which of these two terminals is source or drain. Using the same pointer, we can observe that this terminal is at low potential as compared to this one, so this has to be a source and this has to be a drain. Here the VGS again is 0, which is less than VTH, therefore device is off. Now let's do the part 3. In the part 3 we have a voltage source on the gate which is equal to 1 volts, and again we have to determine which of these two terminals is source and the drain. Well, they are both at the same potential, so we can take either of them to be source or drain. Let me just take this to be a source and this to be a drain, and if I find VGS from this configuration, I'll get is 1 minus 0.2, which is 0.8. Now that VGS is greater than VTH, which was 0.4, so we can say that device is on. Now that we know the device is on, we need to determine the region of operation for this transistor. We know that for the transistor to operate in saturation region, the VDS has to be greater than or equal to VGS minus VTH. Here the VDS is this voltage, which is 0, because on both terminals the voltage is same, which is 0.2. So this terminal, this voltage is 0. VGS in our example is 0.8 at the moment, and the VTH is 0.4. From here we can see that this inequality does not hold true, so therefore device is in linear, also known as triode region. Now we are left with the last part, which is the part D. Here again we can see that the gate terminal is connected to the battery of 1 volt, so we have VG equal to 1 volt. Again we have to decide which of these is source and which of these is drain. We can see that this terminal is at low potential, so therefore it is source, and this one is a high potential as compared to this terminal, so therefore this is drain. Now we can find VGS. VGS is going to be VG minus VS. VG is 1 volt, VS is 0.2 volts, it's 1 minus 0.2 volts, which is equal to 0.8 volts. Now that VGS is greater than VTH, so therefore device is on. Now that we have realized a device is on, we need to check which region of operation is this device M1 working. And we know that device operates in a saturation region if VDS is greater than or equal to VGS minus VTH. Here the VDS is this voltage, which is VD minus VS, which is 0.7 minus 0.2, which turns out to be 0.5. And the VGS in our example is 0.8, and the VTH was 0.4, which results into 0.4, and we can see that this inequality remains intact because 0.5 is greater than or equal greater than 0.4. So we can say that device is operating in saturation region. The second question that I have to solve is 6.28, and I'm going to do 2 parts of it. Let's just take the first part at the moment. In this question, we have to plot Ix as a function of Vx, where Vx goes from 0 to VDD, which is 1.8. So we have something like this, that we have to plot Ix against the Vx, where Vx goes from 0 to, let's just say, VDD, which is 1.8 volts. Here the channel length modulation is assumed to be 0, that is not present, and we also need to determine the value Vx at which the device changes its region of operation, that is when it moves from triode to saturation or vice versa. So let's just move on. To start off, let me just label a few things here. As this is an NMOS, so let's just see which of these two terminal is source. Well, in the case of NMOS, the source has to be at the load potential, so this terminal is going to be the source because this is at load potential as compared to this terminal, and this is going to be drain, and this obviously is going to be a gate. Here VD is 1 volts and the Vs is 0 volts, and the Vg is varying from 0 to 1.88. So let's write all these things here. So VD is 1 volt, Vs is 0 volts, and Vg varies from 0 to 1.8 volts. Now that Vs is 0 volt, therefore Vgs is equal to Vg, because Vgs is Vg minus Vs, and because Vs is 0, so therefore Vgs is actually Vs. So when I vary Vg from 0 to 1.8, I am actually varying Vgs from 0 to 1.8. Here remember that the VTH is given at the start of the problems, which is 0.4 volts. Now let me just draw a table here. So on the very first column, I am going to put in the values, possible values of VGS, which I know is actually equal to Vg, and as I know that Vg is connected to the Vx, so therefore Vgs is actually equal to Vx. And on the second column, I am going to decide if the device is on or off. And we know that device is going to be on only if VGS is greater than VTH. So let's just presume the value of Vx to be 0. If Vx is 0, Vgs is 0, and Vgs which is 0 is less than Vth, so therefore device is off. Let's take another value of Vx, which is Vgs also, to be 0.4 volts. If Vgs is 0.4 volt, then again this relationship is not valid because 0.4 is not greater than 0.4, therefore device is again off. Now if Vgs is 0.5 volts, then we have 0.5 volts here, which happens to be greater than Vth, which is 0.4, therefore this inequality holds true, and you can say the device is turned on now. Now let's just take another value of Vgs like 1.8 volt. If Vgs is 1.8 volt, then we know that 1.8 is greater than 0.4, therefore device is on. So you can see that the device turns on the moment Vx reaches 0.4 or above. So here we can see that if this is 1.8, we can call this thing as 0.4. So device is off before that. If device is off, there is no current. So for all these values of Vx, the current is 0 because device is off, and I can label this point also as Vth because Vth was 0.4. Now that we have realized that device is on in these ranges of the voltages, let's just see what mode is device operating at in this voltage range. So let's just see which mode is device operating, saturation or triode. Well, as the device is off, so we don't have to just test this region of operation in these two cases because device is off. Now that device is on, let's just see which region of operation is this device working. At this moment, the VGS is 0.5. Now the device is in the saturation region if VDS happens to be greater than or equal to VGS minus VTH. Here the VDS is always fixed to 1 volt. Now VGS at the moment for this case is 0.5 and the VTH is always 0.4. Now if I plug in these values in these variables, what I say is I'll get 1 volt on this side and I'll get 0.9 volt on this side, and obviously 1 volt is greater than 0.9 volt, therefore we can decide the device is actually in the saturation region when VGS or Vx was 0.5 volt. Now let me add another value here. Let's just say 1.3 maybe. Now if VGS is 1.3, greater than VTH, device is on, and in this case the VDS is again 1 volt. The VGS is, as mentioned over here, 1.3 volts, and VTH is always 0.4 volts. Now that results into 0.9, and here we have 1 volt. Now here the inequality also holds true, so we can say, but for this value of Vx, device is also on and working in the saturation region. Now let's just take the last one. Here the VDS is again 1 volt and the VGS for this case is 1.8 volts and the VTH for this case is 0.4 volts, and that results into 1.4 volts. And now we can see something happening here. We can see that 1 volt is not greater than 1.4 volt. So this actually is a case of triode region because this inequality is not true. So we can see that at this point the device is operating in triode region, and from 0.5 onwards to 1.3 and something like that, the device is in the saturation region. So we need to find the boundary. We need to find the boundary where the device changes its state or region of operation from saturation to triode or vice versa. Let's just plug in the value of Vx to be 1.4 volts. If Vx is 1.4 volts, device is on, then VDS, let's just see if that inequality is true or not. VDS is fixed to 1 volt, VGS now is 1.4 volts, VTH is 0.4 volt, that results into 1 volt. We can observe that this 1 volt is equal to 1 volt. The inequality or the equality holds true. So we can say that this is operating at saturation region. And if I reduce, this is interesting. Let's just take another value for the sake of it. I mean, I should have put all this thing in a descending or ascending order, but now that I've missed it, let's just keep on moving. Let's just take, so what we have realized is that, let's just take 1.5 volt. So now Vx is 1.5 volt, device is on because 1.5 VGS is greater than 0.4 volt. Now let's just see what VDS is. VDS is fixed to 1 volt and VGS minus VTH. VGS is 1.5 volts and VTH is 0.4 volt. That turns out to be why am I getting the same answer? Why is it it's 1.1. So this inequality does not hold true. So we can say that we are in a triode region. So from here we can see something interesting happening. What we can see is 1.4 volt is the value of Vx where the device is going to change its region of operation. So when Vx happens to be 1.4 volts, let me draw this thing actually closer to the 1.8. This is 1.4. So before 1.4 in this region and ahead of 0.4, I can safely say that device is operating in the saturation region because we already have checked it here, and with 1.3, also at 0.5 it was working in a saturation region. Now as it exceeds 1.4 and let's say it hits 1.5, it changes the mode of operation to a triode. So in this range the device is operating in triode region, also known as a linear region. Now that we have identified the region of operation, now we need to plot the Ix graph. Now this is very important. We all know that the equation for Ix in the case of triode region is given by half mu n C of W over L to VGS minus VTH VDS plus VDS square, and the equation for saturation region is Ix or ID is half mu n C ox W over L VGS minus VTH whole square. So in this region of operation, or we need to plot this red curve, and in this region we need to plot this green curve. Let's just plot this Ix for this region. Here the Vx is equal to Vgs, so the line that is the variable that is varying is this is equal to Vx. You can see it from here. So if I vary Vx, Ix varies, and this is how it should vary. I can see that the Ix varies with Vx as in a quadratic fashion, so therefore the graph is going to go up. Now once I hit this value of Vx, which is 1.4 volt, the mode of operation of transistor or device has changed to triode, so therefore I have to use this equation. Here the Vgs is here, which is Vx. So again you can see that Ix now is kind of a linear function of Vx. So therefore in this window the graph, in this window the graph of Ix and Vx is going to be something like a straight line. So that corresponds to this one, and that one corresponds to this one. So now that we have solved the part A, let's move to the part B. Here again we have to draw this curve of Vx and Ix. Here we can see that again we have an NMOS device. We need to decide which of these two legs is source and which of these two legs is drain. In the case of NMOS, source is always at the low potential. So we can see that this terminal is at low potential as compared to this one, because this is going to vary from 0 to 1.8 volt. So we can label this one as source, this as a drain, and this obviously is a gate. From this labeling we can realize that Vg is always 1 volts, Vs is also fixed to 0 volts. The thing which is varying is Vd, which varies from 0 to 1.8 volts. Now let's just see, first thing first, is the device on or off? Well, the device will be on if Vgs is greater than Vth. Here remember that the Vth is also 0.4 as was in the part A. Here the Vgs is found to be 1 minus 0, which is 1 volts, and the Vth is given to be 0.4. This inequality holds true, therefore device is on. Now that we can also observe that this condition is going to be always hold true, because this is fixed, so there is no way that device is going to turn off. So I can make a comment that device never turns off. Now that we have decided that device is always on, let's just see which mode of operation is device operating and when is it going to change its mode of operation. To do that, again I will need a help of a table. So let's just draw a table. Here I can see that Vd is also equal to Vds, because Vs is 0 from here. So I can say that Vds is actually equal to Vd. So I can plot a Vds on one column, and I know that Vds is equal to Vd, which is actually equal to Vx. And then I have to decide if the device is working in triode or saturation region. So let's just try different voltages here. When Vds is, let's say when Vx is 0 volts, Vds is 0 volts, then VDS should be greater than or equal to VGS minus VTH for device to be in a saturation region. Here the VGS is 1 volts, always 1 volt, and this is always 0.4 volt. So this term is always 0.6 volts. Now that we have set Vx to be 0, which is VDS, so we have 0 volts here. Now this inequality is not true, therefore we are operating in a triode region. Let's just move on and try a value of Vx equal to 0.6 volts. If Vx is 0.6 volts, Vx is same as VDS, we have 0.6 volts, and we always have 0.6 over here, so it's 0.6 volts. This equality holds true, so you can say that we are in a saturation region. Now let's just try another voltage level of Vx. If Vx is 1 volts, we'll have 1 volt here, we always have 0.6 volt here. This inequality is again true, so we are in a saturation region. So we can observe that. Now we need to decide, by the way, we need to decide that, now we can observe that as we increase Vx, we are always in a saturation region. However, when Vx was 0, we were in a triode region. So somewhere between the triode and the saturation region, we need to find the value of Vx where we have switched from this to this region. So let me just see if it's 0.5 volts here. If Vx is 0.5, VDS is 0.5, and we have always 0.6 here, we have an inequality which is not true, therefore we are in a triode region. So from here I can say that this is the value of Vx where the device changes its mode of operation. So let me just label this axis. This is VDD, which is 1.8 volts, and let me just say this is 0.6 volts, which we can also write like VGS minus VTH, because this is 0.4 and this is 1 volt, so this turns out to be 0.6 volts. So this point is VGS minus VTH, this point is VDD. The device is always on, but before that, in this region, the device operates in a triode region, and beyond this, the device operates in saturation region. So now that we have decided the mode of operation of MOSFETs, let's just draw their current Ix curves. We know that in the case of triode region, the Ix is half mu n Cox W over L 2 VGS minus VTH VDS plus VDS square, and for the case of saturation region, the Ix turns out to be half mu n Cox W over L VGS minus VTH square. Now here we observe that VDS is the voltage that is varying, so we can say that this variable and this variable are varying, and over here there is no VDS, so Ix remain constant for all values of VDS. So we can say that Ix remain constant for all values of VDS, which is Vx, and in the triode region we can see that Ix is going to behave in a quadratic fashion because we have a square over here. So we can say that the graph is going to be something like this. Where this is the point where the mode of operation changes. Now this is the last question of this problem solving session. This is question number 630 of our textbook. Here We are given few parameters. We have assumed there is channel length modulation. We need to find the value of VB when the transistor is right at the edge of saturation region. So let's just try to label the current ID, and because this is an NMOS device, because arrow is pointing outwards, and in the case of NMOS the source is always at low potential. So this one is source and this one is drain, and this one is our VDS. If I apply KVL in this loop, what I get is VDD minus IDRD minus VDS equal to 0. Now let me rearrange this equation. I'll get ID equal to VDD minus VDS over RD. Now what is the value of VDS at which the transistor is at the edge of saturation? Well, that value of VDS is actually VDS equal to VGS minus VTH. So I can write this equation as VDD minus VGS plus VTH divided by RD, which is equal to ID. Now although I want to be at the edge of saturation, but still I am in the region of saturation, so I can approximate this ID current to be half mu n Cox W over L VGS minus VTH whole square. I don't think if I need this bracket, and because we have assumed channel length modulation, so we have to append 1 plus lambda VDS as well. Here we can observe that VGS is actually VB, because looking at this side we can see that this is our VGS, which actually is VG because VS is 0, and the VG is VB. So if I plug in the value of VGS to be VB in all of this equation, I'll end up with VDD minus VB plus VTH over RD equals to half mu n Cox W over L VB minus VTH whole square 1 plus lambda VDS. Now here this quantity is known, this is given, all of this stuff is given, this is also given, and we are sure about this one as well. So now to find the value of VB, we need to solve this equation iteratively, and if we do that, we'll end up with VB equals to 0.57 volts, and if I plug in this value of VB into the equation of ID, this one or this one, I'll get the value of ID to be 0.33 milliampere. That is it. Thank you for listening.